Something is moving through our solar system right now, and it's not following the rules. You can't see it with your naked eye. But across the world, in observatories perched on Chilean mountaintops, in domes scattered across the Hawaiian Islands, astronomers are watching. They're tracking an object that came from beyond our solar system. A wanderer that's supposed to swing past the sun once and disappear forever into the cold darkness between stars. That's what the math says. That's what should happen. But it's not happening. This object is changing course. Not dramatically, not suddenly, but consistently, steadily. The trajectory is shifting in ways that gravity alone cannot explain. Scientists are measuring directional jets, watching debris release in organised patterns, and seeing something that makes them uncomfortable controlled acceleration. Some are quietly asking a question no one wants to say out loud. On December 19th, 8 days from now, we get our clearest view ever. Every major telescope will turn toward this visitor as it makes its closest approach to Earth. What they see will either explain everything or make this mystery far stranger than anyone imagined. Let me show you what's really happening out there. Before we dive deeper, you need to subscribe right now, and here's exactly why. We're tracking this object in real time as it approaches. Updates are coming fast. On December 19th, we're posting live coverage of the observations as they happen. This is one of those rare moments in astronomy where we might actually witness something change what we thought we knew about our universe. You deserve to be here when it happens. Hit subscribe, turn on notifications, and let's follow this together. When astronomers first spotted this visitor back in September, they did what they always do. They measured its position. They tracked its movement across the sky. They calculated where it came from and where it was going. This is standard procedure routine work that's been done thousands of times with thousands of objects. You plot the course, you run the numbers, and the math tells you exactly what happens next. And for weeks, everything made sense. The object was moving on what's called a hyperbolic orbit. Think of it like throwing a ball into the air. Gravity pulls it up in a curve, then pulls it back down. But if you throw it fast enough, really fast, it doesn't come back down. It just keeps going, curved by gravity but never captured by it. That's a hyperbolic orbit. One passed through our solar system, accelerating as it falls toward the sun, then slinging back out into interstellar space, gone forever. The calculations were clean. The trajectory was predictable. This visitor would reach its closest point to the sun on December 12th, then begin its long journey back into the darkness between stars. Scientists could tell you exactly where it would be on any given day, down to the kilometre. But then, something changed. On December 5th, astronomers noticed the object wasn't quite where it was supposed to be. Not by much. We're talking about a deviation measured in arc-seconds, tiny fractions of a degree in the sky. You and I would never notice. But to someone tracking an object millions of miles away with mathematical precision, it stood out immediately. They checked their calculations. They recalibrated their instruments. They looked for errors in the data. There weren't any. The object had moved off its predicted path. And it wasn't a one-time glitch. It was consistent, ongoing. The deviation was growing. Dr. Marco Micheli from the European Space Agency was one of the first to confirm it. He released a statement that used very careful language. We are observing non-gravitational acceleration in the object's trajectory. Let me translate what that means. When something moves through space, gravity is supposed to be the only thing changing its path. The pull from the sun, the tug from planets, all perfectly calculable. Non-gravitational acceleration means something else is pushing or pulling on the object, something the math didn't account for. Now, this isn't necessarily unusual. Comets do this all the time. As they heat up near the sun, ice turns to gas. The gas bursts out through cracks in the surface, creating jets. Those jets work like tiny rocket engines, giving the comet a push. It's called outgassing, and it's a natural process. But here's what made Michelli's statement significant. He didn't just say they were seeing non-gravitational acceleration. He said the magnitude and consistency were unusual. Magnitude means strength. The push this object is experiencing is stronger than what you'd normally expect from random outgassing. Consistency means pattern. Normal outgassing is chaotic. A comet tumbles as it moves. Vents open and close randomly. The thrust comes in bursts from different directions, creating a wobbly, unpredictable path. This object, the acceleration is steady, controlled. The deviation from the predicted path isn't random, it's following a pattern. Imagine you're watching someone throw a football. It spins through the air in a smooth arc, exactly where you'd expect based on the throw. Then, mid-flight, it shifts, not bouncing off anything, not caught by wind, just adjusting, moving on a slightly different curve than physics alone would create. That's what astronomers are watching right now. And it's making them nervous, because there are really only two explanations. Either this is a natural phenomenon we don't fully understand, yet some unique combination of the object's shape, rotation and composition creating this effect, or something about this object is fundamentally different from what we've seen before. The data from December 5th wasn't an isolated observation. Follow-up measurements from observatories in Chile, Hawaii, and the Canary Islands all confirmed the same thing. The object's position continues to diverge from the calculated hyperbolic path. Not dramatically, not in a way that suggests it's going to do anything dangerous, but measurably, undeniably. Scientists started running simulations. What kind of outgassing pattern would create this specific type of acceleration? What shape would the object need to be? How fast would it need to be spinning? They fed different variables into the models, trying to find a natural explanation that fit the observations. Some models worked. Kind of. You could create scenarios where irregular venting from a weirdly shaped object, rotating at just the right speed, might produce something close to what they were seeing. But those scenarios required a lot of coincidences. A very specific shape, a very specific rotation rate, vents positioned in very specific locations, all firing in very specific patterns. Possible? Yes. Likely that's the question astronomers are quietly debating right now. What makes this even more intriguing is the timing. The most significant acceleration occurred right around perihelion, the moment of closest approach to the Sun. That's when a comet experiences maximum heating. That's when you'd expect the strongest outgassing. So on one hand, the timing makes perfect sense. On the other hand, the precision is almost too perfect. Maximum heat triggers maximum thrust, producing maximum course adjustment at exactly the moment when gravitational forces are also at their strongest, allowing the object to make the most efficient change to its trajectory with the least amount of energy. If you were planning this, if you were designing a trajectory adjustment, this is exactly when you do it. But we're getting ahead of ourselves. Let's stick with what we can measure, what we can verify. The trajectory has changed. The acceleration is consistent. And in 8 days, when this object makes its closest approach to Earth, we're going to get our best opportunity to understand why. Because right now, despite all our instruments, all our calculations, all our observations, we still can't see the object itself clearly enough to know what we're really looking at. Right now, as you're listening to this, there's an object 180 million miles away that we can barely see. Not because it's small, it's estimated to be somewhere between 3 and 5 kilometers wide, roughly the size of a mountain. We can't see it clearly because it's wrapped in a thick cloud of gas and dust, glowing from the sun's heat, obscuring the solid nucleus underneath. It's like trying to identify someone standing behind frosted glass. You see the outline, you see movement, but you can't make out the details that would tell you what you're really looking at. That changes on December 19th. On that date, this visitor reaches its closest point to Earth 1.88 astronomical units away. To put that in perspective, 1 astronomical unit is the distance from Earth to the Sun, about 93 million miles. So we're talking about roughly 175 million miles. Still incredibly far. You're not going to see this with binoculars from your backyard, but for the Hubble Space Telescope, for the Very Large Telescope in Chile, for the Keck Observatory in Hawaii, that's close enough to see details we've never been able to resolve before. And here's why December 19th is special beyond just distance. It's about geometry. Right now, we're looking at this object almost head-on as it moves toward us. Imagine a car driving straight at you with its headlights on. All you see is glare. You can't tell what kind of car it is, what colour, whether it's damaged. But when that car passes and you see it from the side, suddenly all those details become visible. On December 19th, the viewing angle shifts. The sun will be lighting the object from the side rather than from behind. That side lighting reveals texture, shape, and surface features that are invisible in direct light. The gas cloud that's currently hiding the nucleus will thin out as the object moves away from perihelion, and we'll finally be able to see through it. Scientists are waiting for 3 specific things. First, the shape. This might sound simple, but it's crucial. Natural comets are ugly. They're irregular, lumpy, asymmetric, basically rubble piles of ice and rock held together by weak gravity. Think of Comet 67P, the one the Rosetta mission studied up close. It looked like a rubber duck, 2 lobes stuck together, covered in boulders and pits. That's normal. But what if this object isn't irregular? What if the enhanced observations on December 19th reveal something smooth, cylindrical, symmetrical? That would be a problem. Natural processes don't create clean geometric shapes. Erosion makes things rounded, yes, but also pitted and uneven. If this object has defined edges, smooth surfaces, or any kind of geometric regularity, we're looking at something that challenges our understanding of how these bodies form. The second thing they're watching for is rotation rate. Every object in space spins, it's unavoidable. When material collapses to form a comet or asteroid, any tiny asymmetry in that collapse creates rotation. And because space is a vacuum with no friction, that spin continues essentially forever. For most comets, you can measure rotation by watching brightness changes. As the irregular shape tumbles, different surfaces reflect different amounts of light. The comet gets brighter, then dimmer, then brighter again in a predictable cycle. Comet Halley, for example, rotates once every 52 hours. Comet 67P takes about 12 hours. But with this object, we're not seeing those brightness variations. The light output is remarkably steady. Why does that matter? Because steady outgassing, the kind producing the consistent acceleration we talked about earlier, shouldn't be possible on a fast-tumbling object. The vents would be pointing in different directions as the object spins, creating thrust in random directions, not a steady push, for the acceleration pattern to make sense naturally. The object would need to be either spinning very slowly, or somehow oriented so that the active vents stay pointed in the same direction relative to its motion. On December 19th, with better resolution, astronomers will finally be able to detect those brightness variations if they exist. They'll measure the rotation period. And if it turns out this thing is barely spinning, or spinning in a suspiciously convenient orientation, that adds another layer to the mystery. The third observation, and perhaps the most important, is watching for course corrections. Here's something most people don't realize about orbital mechanics. Earth's gravity matters. even at 175 million miles, our planet exerts a small but measurable gravitational pull on passing objects. It's not enough to capture something moving this fast, but it is enough to slightly alter the trajectory. If this object is going to make another adjustment to its path, whether through natural outgassing or something else, the most efficient time to do it is during closest approach. That's when gravitational forces from both the Sun and Earth are acting on it, when any small thrust produces the maximum change in trajectory. Astronomers will be measuring the object's position with extraordinary precision throughout December 19th and the days following. They're looking for any deviation from the predicted path, any acceleration spike, any sign that something is actively influencing where this object goes next. Think about what that means for a moment. We have an object that's already shown unexpected trajectory changes. We're about to watch it pass through a gravitational environment where course adjustments would be most effective, and we'll have every major telescope trained on it, measuring everything we possibly can. If it's just a comet behaving strangely due to natural processes, December 19th should help us understand those processes better. We'll see the shape, measure the spin, watch how the outgassing responds to changing solar heating as it moves away from the Sun. But if something else is happening, if this object does something that can't be explained by natural comet behaviour, we'll see that too. We'll have the data, the observations, the measurements. There won't be ambiguity. The observation campaign is already planned. Teams are coordinated across multiple observatories. Space telescopes have dedicated time slots. Radio telescopes are standing by in case there's any detectable emission. Even amateur astronomer networks have been mobilized to provide continuous coverage as Earth rotates. 8 days from now, we're going to learn something definitive about this visitor, and depending on what we learn, we might need to completely rethink what we thought we knew about objects travelling between the stars. But before we get to that day, there's something else about this object that's been bothering scientists since the very beginning. Something it's leaving behind as it passes through our neighbourhood. When a comet passes through the inner solar system, it doesn't just visit its sheds constantly. The Sun's heat turns ice into gas, and that gas carries material with it. Dust particles, tiny fragments, microscopic grains. Most of it gets blown away by solar radiation pressure, scattered into space, gone within weeks. But this visitor is doing something different. It's releasing heavy material. Not just dust. We're talking about particles the size of pebbles, gravel, small rocks. And here's the critical detail: heavy particles don't blow away. They're too massive for sunlight to push them out of the solar system. Instead, they do something else entirely. They stay. Doctor Paul Chodas, who directs NASA's Center for Near-Earth Object Studies, ran the calculations after analysing the debris signature. His team used models that track how particles of different sizes behave after being released from a moving object. The results were published in a preliminary report in early December, and one finding stood out immediately. Debris from this object, specifically particles larger than 1 centimetre, will remain in orbits within our solar system. Some of that debris is already crossing Earth's orbital path, and more will continue to intersect our planet's trajectory starting in late 2026. Let me be very clear about what this means and what it doesn't mean. This is not an impact threat. We're not talking about the object itself hitting Earth, and we're not talking about dangerous asteroid-sized chunks. We're talking about a debris stream. Think of it like the trail that creates meteor showers. You've probably seen meteor showers before. The Perseids in August, the Geminids in December. Those happen when Earth passes through debris trails left by comets that visited our solar system hundreds or thousands of years ago. Tiny particles, most smaller than a grain of sand, burning up as they hit our atmosphere at tens of thousands of miles per hour. Beautiful, harmless. This should be the same thing, in theory. But here's what's unusual. When scientists analysed the pattern of debris release, they found something unexpected. Normal comets shed material randomly. As the nucleus rotates and tumbles, different parts face the sun at different times. Vents open and close chaotically. The result is debris scattered in all directions, creating a broad, diffuse trail. This object is releasing material in concentrated bursts. Directional jets. Think about the difference. Imagine someone walking through a park scattering seeds. If they're just tossing handfuls randomly, seeds land everywhere in a wide, irregular pattern. But if they're using a spreader, walking in deliberate lines, the seeds land in organised rows with specific spacing. The debris from this visitor shows organisation. Spectroscopic analysis studying the light signature of the material being released reveals distinct episodes of activity. On December 7th, instruments detected a significant burst of particle emission. Then another on December 10th. These weren't continuous releases, they were events, discrete, timed. And here's the detail that makes scientists uncomfortable. One of the largest bursts occurred within hours after perihelion passage on December 12th, right at the moment of maximum solar heating. Right when the object experienced the strongest gravitational pull from the sun. Right when it would be most efficient to release material into stable orbits. The timing, once again, is almost too precise. Dr. Chodas's team modelled what those stable orbits look like. They found that debris released at perihelion with the observed velocities will settle into elliptical paths that bring them back through the inner solar system repeatedly. Some will cross Mars's orbit, some will cross Earth's, a few trajectories even intersect Venus. Now, is this possible naturally? Yes. Comets have been depositing debris in our solar system for billions of years. That's where meteor showers come from. That's where zodiacal dust comes from, that faint glow you can sometimes see in the night sky along the plane of the solar system. But natural debris deposition is usually accidental. It's a byproduct of solar heating. The comet doesn't choose where its debris goes. It just sheds material, and that material drifts into whatever orbits physics dictates based on velocity and position at release. This looks different. The bursts are timed. The velocities are consistent. The resulting orbits show patterns. If you are designing a mission to deposit material in another star system, let's say for scientific study, or resource mapping, or even as markers for future reference, how would you do it? You'd probably coat your probe in ice to protect it during the million-year journey through interstellar space. You'd time your material releases to coincide with gravitational assists. You'd use the star's heat to trigger controlled venting, releasing payloads at precise moments to achieve desired orbits. You'd make sure those orbits were stable, crossing the paths of potentially interesting planets, ensuring the material would persist for thousands of years. And you'd make the whole thing look like a comet, because comets releasing debris is normal. Expected. Nothing that would raise immediate suspicion. I want to stress something here. I'm not saying that's what's happening. I'm saying that's what the pattern resembles. And that resemblance is what's making some scientists very quiet when they discuss this object in professional settings. There's also another aspect to consider. The composition of the debris matters. Preliminary spectroscopy shows high concentrations of carbon-based molecules, silicates, and what appear to be complex organic compounds. These are the building blocks of chemistry materials that, under the right conditions, can participate in reactions that lead to more complex structures. Are we looking at contamination? Is this visitor potentially carrying material that could, theoretically, influence the chemistry of bodies it encounters? Again, This happens naturally. Comets have been delivering organic molecules to planets for billions of years. Earth's early oceans were likely enriched by comet impacts. Mars received similar deliveries. The moons of Jupiter and Saturn, too. It's part of how solar systems evolve chemically. But the concentration here is notable. And the fact that this material is being deposited in stable, long-lasting orbits that will intersect multiple planetary paths over the coming centuries that adds a dimension to this story that goes beyond simple astronomical curiosity. By 2026, Earth will begin passing through the densest parts of this debris stream. We'll see meteor activity. Scientists will be able to collect samples from the upper atmosphere using high-altitude aircraft, the same way they've collected samples from other meteor streams. We'll be able to analyze the material directly, study its chemistry in detail, understand exactly what this visitor brought with it from beyond our solar system. But that's 2 years away. Right now, there's something else about this object that's been visible since the very beginning, something that appears in almost every telescopic image, and something that shouldn't exist the way it does a feature that's been quietly troubling astronomers since the first observations. Look at any photograph of this object taken in the last 3 months, and you'll see something strange. There's the expected tail, a broad, fuzzy stream of gas and dust flowing away from the sun. Exactly like every comet you've ever seen in pictures. That's normal. Solar radiation pushes material away from the nucleus, creating that classic tail that always points away from the sun, regardless of which direction the comet is travelling. But there's also something pointing the other direction. A narrow spike, thin, almost needle-like, extending from the nucleus directly toward the sun. Astronomers call this an antitail, and while they're not completely unheard of, they're rare, and they're definitely not supposed to look like this. Antitails are usually optical illusions. Here's how they normally form. Imagine a comet with a broad, flat debris disk material spread out in the plane of its orbit. When we view that disk edge on from Earth, it can appear as a spike pointing in an unusual direction, including seemingly toward the sun. But it's not actually pointing that way. It's a perspective trick, like how a tilted dinner plate looks like a line when you view it from the edge. Those illusions disappear when the viewing angle changes. They're temporary, fleeting, visible for a few days at most as Earth moves in its orbit and our perspective shifts. This antitail has been visible for 3 months. It hasn't faded. It hasn't changed orientation despite our shifting viewpoint. And according to detailed imaging from the Gemini Observatory in Hawaii, it's not a perspective effect. It's real material, physically extending from the nucleus toward the sun. That shouldn't be stable. Think about the forces at work here. Solar radiation pushes outward. Solar wind, a stream of charged particles flowing from the sun, also pushes outward. Everything should be blown away from the sun. Maintaining a structure pointing toward the sun is like trying to hold an umbrella steady in a hurricane while the wind is trying to rip it from your hands and flip it inside out. Yet this spike persists. Images from December 8th show it clearly. Images from December 15th show it's still there. Same orientation, same structure. Doctor. David Farnokia from NASA's Jet Propulsion Laboratory analysed the dynamics in a technical briefing that was shared with other researchers but not widely publicised. He noted something specific. The object is exhibiting predictable non-gravitational forces that suggest a stable venting pattern inconsistent with chaotic tumbling. Let me unpack that carefully phrased statement. When a comet tumbles, which is what natural comets do, vents on its surface point in constantly changing directions. One moment a vent faces the sun and releases gas. Hours later, that same vent points into space. The gas jets fire in random directions as the comet spins, creating unpredictable thrust. But if the venting pattern is stable, that means either the comet isn't tumbling, or the active vents are positioned in such a specific way that their combined thrust stays constant despite rotation. Both scenarios require very particular conditions. Now here's where it gets interesting. That anti-tail isn't just sitting there. It's doing something. When material is ejected toward the sun against the flow of solar radiation, it creates drag. Not atmospheric drag like on Earth, but radiation drag. The photons from sunlight hit the particles and slow them down in space. Where there's no friction, even tiny forces matter, and this anti-tail is producing a tiny but constant force opposing the object's motion. Meanwhile, the main tail, the normal one pointing away from the sun, is being created by jets on the opposite side of the nucleus. Those jets are firing backward relative to the object's direction of travel, creating forward thrust. Do you see what this creates? A thrust system. Jet engines pushing from behind. A drag element providing stability from the front. It's almost like a rocket with attitude control thrusters mechanisms designed to keep spacecraft oriented correctly during flight. In engineering, this is called thrust vectoring. You use multiple engines pointing in different directions to maintain stable, controlled acceleration. It's how rockets fly straight instead of tumbling. It's how spacecraft make precise course corrections. Could this happen naturally? Could random venting on an oddly shaped, conveniently oriented comet coincidentally create this configuration? Technically, yes. Space is vast. Trillions of comets exist in galaxies across the universe. Given enough chances, unlikely configurations will occasionally occur. Maybe we're looking at one of those rare cases where everything lined up just right, the shape, the rotation, the vent positions, the composition to create stable directional thrust. But let's look at historical precedents. How many comets have we studied in detail? Hundreds, at least in basic observations. Dozens with serious telescopic campaigns, a handful with spacecraft visits. Comet Halley, visited by multiple probes in 1986, showed chaotic outgassing. Jets turned on and off as different parts of the nucleus rotated into sunlight. The comet tumbled irregularly. Comet 67P/Churyumov-Gerasimenko, studied up close by the Rosetta spacecraft for 2 years, exhibited complex but clearly random venting. Jets appeared, disappeared, shifted position. The comet's rotation was irregular and changing. Comet McNaught in 2007 developed a spectacular anti-tail, one of the most prominent ever observed. But it was a perspective effect, visible for only a few days, and it didn't persist across changing viewing angles. None showed this combination of features: stable anti-tail, consistent directional thrust, predictable acceleration, all occurring simultaneously in an object that shows no signs of the tumbling that should make such stability impossible. There's another detail worth mentioning. The anti-tail isn't just narrow, it's remarkably straight. Most comet tails show curves, bends, kinks. They respond to changes in solar wind, variations in the comet's outgassing rate, the comet's changing orientation. They're dynamic, flowing structures. This spike maintains its geometry, frame to frame, day to day. It looks less like a diffuse gas stream and more like something being actively collimated, focused into a beam. Collimation requires confinement. On Earth, we collimate light using lenses, gas using nozzles, particles using electromagnetic fields. In space, natural collimation is rare. Magnetic fields around young stars can do it. Black hole jets accomplish it through mechanisms we don't fully understand. But a comet creating a collimated particle beam. There's no obvious natural mechanism, unless the geometry isn't random, unless the structure producing this emission has a shape specifically suited to creating focused output, a nozzle, a channel, a designed aperture. I keep coming back to that word designed, and I keep trying to find natural explanations that avoid it. because the implications of design are uncomfortable. They raise questions we're not sure we're ready to answer. What we do know is this: the anti-tail is there, it's stable, and it's affecting the object's trajectory in ways that combine with the main outgassing to produce the controlled acceleration we've been observing, whether that's profound coincidence or something else. December 19th might help us understand. But even if we get perfect images of the nucleus, even if we measure the rotation precisely, we still need to address perhaps the most puzzling aspect of this entire mystery, the chemistry this visitor is carrying. When astronomers first captured the spectrum of this object, essentially breaking down its light into individual wavelengths, to see what chemicals are present, they expected to see the usual suspects. Water ice, of course. Carbon dioxide, maybe some ammonia. These are the standard ingredients of comets, the icy leftovers from when our solar system formed 4.6 billion years ago. What they found was all of that, plus something more: methanol, hydrogen cyanide, formaldehyde, complex carbon chains, and in concentrations that made the spectroscopy teams double-check their instruments. Now, let me be clear. Finding organic molecules on a comet isn't shocking, we've detected them before. Comet Hale-Bopp in 1997 showed methanol. Comet Hyakutake had ethane and methane. The Rosetta mission found glycine, an amino acid on Comet 67P. Comets are known to carry organic chemistry. That's established science. But the mixture here is different. The ratios are unusual. And when you look at what these specific molecules can do under the right conditions, a fascinating picture emerges. Let's talk about what these chemicals actually are. Without the technical jargon, methanol is a simple alcohol, one carbon atom bonded to 3 hydrogen atoms and 1 oxygen. In Earth's early atmosphere, methanol played a role in creating more complex organic molecules. It's reactive. It participates readily in chemical reactions. Hydrogen cyanide sounds dangerous, and it is in high concentrations on Earth. But in the cold chemistry of space, it's incredibly important. It's one of the key ingredients in creating adenine, one of the nucleotide bases in DNA. In laboratory experiments simulating early Earth conditions, hydrogen cyanide combines with other simple molecules to form amino acids. You might recognize that experiment. In 1952, Stanley Miller and Harold Urey took simple chemicals methane, ammonia, hydrogen, water added energy in the form of electrical sparks to simulate lightning, and created amino acids, the building blocks of proteins, the fundamental components of life. The mixture of chemicals being released by this visitor contains several of the key ingredients from that experiment. Coincidence possibly. Comets formed in the outer reaches of the solar system where these molecules naturally condense from gas. They've been carrying this chemistry for billions of years. Earth's oceans were likely enriched by comet impacts during the late heavy bombardment about 3.9 billion years ago. Those impacts may have delivered the organic molecules that eventually led to the emergence of life. So in one sense, finding these molecules on an interstellar comet makes perfect sense. Chemistry is chemistry. The same elements exist throughout the universe. The same reactions occur under similar conditions. A comet from another star system would naturally carry similar materials to comets from our own. But here's what's giving scientists pause: the concentration and the variety. Spectroscopic analysis from the Keck Observatory in Hawaii, published in a preliminary data release on December 10th, showed emission lines for at least 9 different carbon-bearing molecules. That's exceptionally high diversity for a single object. Most comets show 3 or 4. This one is a chemical library, and the concentrations don't quite match what models predict for a comet formed in a typical stellar system. The ratio of methanol to water is higher than expected. The hydrogen cyanide abundance is elevated. the presence of formaldehyde in measurable quantities alongside complex carbon chains suggests chemistry that's been processed, altered, concentrated. Is it possible this comet formed in an unusual environment, around a star with different composition than our Sun, in a molecular cloud with atypical chemistry? Sure, we've only studied a handful of interstellar objects. We don't know the full range of what's normal. But we also can't ignore what this chemistry represents. These aren't just random molecules, they're precursors, ingredients, the raw materials for building more complex structures that, under the right conditions, liquid water, energy sources, geological activity can start the long climb toward biology. There's a concept in astrobiology called panspermia. The idea is ancient, dating back to Greek philosophers, but the modern version was articulated by scientists like Francis Crick. Yes, the same Crick who discovered DNA's structure and astronomer Fred Hoyle. The basic idea life doesn't originate on just one planet. It spreads. Comets and asteroids carry organic molecules, perhaps even simple microorganisms, between worlds. An impact on one planet ejects material into space. That material survives the cold, radiation-protected journey through space, frozen in ice. Eventually it lands on another world, delivering its chemical or biological cargo. We know this happens. Meteorites from Mars have been found on Earth. Material from Earth has almost certainly reached other planets. Organic molecules can survive in space, especially when embedded in ice. Some bacteria can endure extreme radiation and cold in dormant states. What if interstellar space is part of this cycle? What if comets travelling between star systems are nature's way of distributing the ingredients for life across the galaxy under this framework? This visitor isn't remarkable for carrying organic chemistry. It's doing what comets do, acting as a delivery mechanism for the molecular building blocks that, given a suitable environment, might eventually contribute to the emergence of life. And remember the debris trail we discussed earlier, material being deposited in stable orbits that will intersect Earth. Mars, Venus, possibly even Jupiter's moon Europa. If this visitor is carrying concentrated organic chemistry, that material isn't leaving our solar system, it's staying here. Some of it will eventually fall into planetary atmospheres or impact surfaces. Is this deliberate? Is this visitor specifically designed to seed our solar system with these molecules? Or is this simply what interstellar comets do, naturally distribute chemistry across the galaxy through random motion, with no intent, no design, just the physics of gravity and chemistry happening as it always has? The honest answer is we don't know. Both explanations fit the observations. Natural panspermia is a legitimate scientific theory supported by evidence. But so is the hypothesis that this chemistry is unusually concentrated, unusually diverse, and being distributed in unusually stable orbits. What we can say for certain is this: by late 2026, when Earth begins passing through this debris stream, we'll be able to collect samples. High-altitude research aircraft can scoop particles from the upper atmosphere during meteor showers. NASA has done this before with other meteor streams. We'll be able to analyze the material directly in laboratories, study its chemistry at the molecular level, perhaps even search for complex organic structures we can't detect from a distance. We'll know exactly what this visitor brought with it from beyond our solar system. And depending on what we find, we might have to reconsider some fundamental assumptions about how chemistry moves through the galaxy and what role these wandering objects play in the story of life spreading across the cosmos. But to understand why this particular chemistry matters so much, why these specific molecules in these specific concentrations are raising so many questions, we need to address something we've been carefully avoiding: the fact that we still can't answer a basic question about this object. How fast is it spinning? Every object in space rotates. It's unavoidable. When clouds of gas and dust collapse to form stars, planets, asteroids, comets, any kind of celestial body, even the tiniest asymmetry in that collapse creates angular momentum. And because space is essentially frictionless, that spin continues indefinitely. For asteroids and comets, rotation is often chaotic. These objects aren't perfectly round. They're irregular chunks of rock and ice, sometimes barely held together by their own weak gravity. As they spin, different faces catch sunlight at different angles, reflecting varying amounts of light back toward Earth. That variation in brightness is how we measure rotation. Astronomers take images over several hours or days, plot the brightness changes on a graph, and the pattern reveals the rotation period. For Comet Halley, it's about 52 hours per rotation. For asteroid Bennu, studied extensively by NASA's OSIRIS-REx mission, it's 4.3 hours. Even the famous interstellar visitor Oumuamua, despite all its mysteries, showed clear brightness variations indicating a tumbling rotation of roughly 8 hours. This object shows almost none. The brightness is remarkably steady. Not completely flat, there are minor fluctuations, but nothing like the pronounced variations you'd expect from an irregularly shaped body tumbling through space. Why does this matter beyond simple curiosity? Because rotation rate is directly connected to the outgassing behaviour we've been discussing, let me walk you through the physics. Imagine a comet nucleus with several active vents, places where ice is turning to gas and escaping into space. If the comet is rotating quickly, those vents constantly change their orientation relative to the Sun. One moment a vent faces the Sun directly, receiving maximum heating, producing maximum gas output. A few hours later, as the comet rotates, that same vent points into shadow. It cools, the gas output drops or stops entirely. This creates pulse thrust, bursts of push in varying directions as different vents activate and deactivate during each rotation cycle. The result is a wobbly, unpredictable trajectory, exactly what we see in most active comets. But remember, the trajectory data from Part 1, the acceleration this object is experiencing, isn't wobbly. It's smooth, consistent, directional. For that to happen naturally, one of three things must be true. First possibility, the object is rotating extremely slowly. So slowly that active vents stay oriented in roughly the same direction for extended periods, creating sustained thrust rather than pulses. But slow rotation creates a different problem. Solar heating is intense. If one side of a comet faces the Sun continuously for days or weeks, it experiences extreme thermal stress. The Sun-facing side heats up dramatically while the shadow side stays frozen. That temperature difference causes structural cracking, asymmetric outgassing, eventually surface collapse. We should see dramatic changes in the object's appearance and behaviour. We're not seeing that. Second possibility, the object is rotating, but it's perfectly spherical. A sphere reflects the same amount of light regardless of rotation, so we wouldn't see brightness changes, except natural comets aren't spherical. The Rosetta mission showed us that Comet 67P looked like a rubber duck. Images of other comets reveal potatoes, peanuts, irregular lumps. Gravitational forces and random collisions during formation create asymmetric shapes. A perfectly spherical comet would be extraordinary, potentially unprecedented. Third possibility, the object is rotating and it's not spherical, but the rotation axis happens to point almost directly at us. Think of watching a spinning top from directly above. You see it spinning, but the outline doesn't change. The brightness stays constant because the same profile faces you throughout the rotation. This is technically possible, but it requires remarkable coincidence, the object's rotation axis aligned with our viewing angle to within a few degrees. And that alignment would need to be maintained as both the object and Earth move through their respective orbits. What are the odds of that statistically? Quite low. Out of thousands of observed comets, we've seen this type of alignment occasionally, but it's rare. And those cases typically reveal themselves over time as viewing angles gradually shift. Here we are, 3 months into observations, and the brightness remains suspiciously stable. There's another clue in the data. When astronomers study comets, they don't just measure brightness, they measure how that brightness varies across different wavelengths of light. Different molecules emit different colours when heated. By analysing the spectrum of emitted light, you can map which parts of the nucleus are active. For this object, the emission spectrum is unusually uniform. The hydrogen cyanide signal comes from the same direction as the methanol signal, the water signal, the carbon dioxide signal. Everything seems to be venting from the same region of the nucleus, or at least from regions that maintain consistent orientation. In natural comets, different chemicals often vent from different locations because composition isn't uniform across the surface. You get patches of water ice here, carbon dioxide ice there, areas rich in organics somewhere else. As the comet rotates, different chemical signatures appear and fade as those patches rotate in and out of sunlight. This homogeneity, this consistent, multi-wavelength emission from apparently stable sources is unusual. Dr. Matthew Knight from the US Naval Observatory, who specialises in cometary dynamics, published observations from December 3rd through December 14th. In his data summary, he noted, "The light curve shows minimal amplitude variation inconsistent with significant shape asymmetry or uncontrolled tumbling. Rotation state remains poorly constrained." Poorly constrained is scientists speak for "we don't know." And the fact that we don't know is itself informative. With modern instruments, determining rotation periods for comets is routine. We do it constantly. The fact that this object has resisted straightforward characterization for 3 months suggests something about it is genuinely different. Could it be oriented flight? The term sounds technical, but the concept is simple. Instead of tumbling chaotically like natural debris, the object maintains a stable attitude, a consistent orientation relative to its direction of travel and the sun. Spacecraft do this. Satellites do this. They use reaction wheels, thrusters, or even passive systems like gravity gradient stabilization to keep specific surfaces pointed in specific directions. It allows solar panels to face the sun continuously, antennas to point toward Earth, scientific instruments to target their subjects. But comets aren't supposed to do this. They're chunks of ice and rock. They don't have control systems. They tumble. Unless, and this is speculation that some scientists are quietly entertaining, unless the mass distribution inside this object isn't random, unless there's some kind of internal structure that creates natural stabilization, or unless we're misunderstanding what we're looking at entirely. December 19th should help clarify this. With improved resolution and continuous monitoring over several days, astronomers will have their best opportunity to detect rotation. If there are brightness changes, even subtle ones, the pattern will emerge. If the object is somehow maintaining oriented flight, that will become apparent too. But here's the uncomfortable question: what if the answer is neither? What if December 19th shows us an object that's clearly not tumbling, clearly not spherical, and clearly maintaining stable orientation through mechanisms we can't identify? Where does that leave our understanding? And more importantly, how do we reconcile that with everything else? We've observed the trajectory adjustments, the debris pattern, the chemistry, the anti-tail. At some point, the accumulation of unusual features stops looking like coincidence and starts looking like something we need to take seriously, even if we're not sure what that something is. At this point, we've covered the observations, the trajectory anomaly, the debris trail, the anti-tail, the chemistry, the rotation mystery. Each piece taken individually has possible natural explanations. But when you step back and look at everything together, you're faced with a question that doesn't have an easy answer. What are we actually looking at? The scientific community, at least in public discussions, has settled into 3 broad frameworks for interpreting this object. Let me walk you through each one, along with the evidence supporting it and the problems it faces. Scenario 1. It's a normal comet. This is the official position of most major astronomical organisations. Yes, the object exhibits unusual characteristics. Yes, the behaviour is outside the typical range we've observed, but comets are inherently variable. We've studied thousands of comets from our own solar system, but only 3 confirmed interstellar objects. Our sample size for interstellar visitors is vanishingly small. Maybe this is simply what comets from other stellar systems look like. Different formation environments, different chemical compositions, different structural properties. The star this comet formed around might have been richer in heavy elements than our Sun, creating ices with unusual chemistry. The molecular cloud it condensed from might have had atypical ratios of organic molecules, the steady outgassing. Perhaps this comet has an unusually uniform composition, creating consistent venting patterns. The anti-tail. Maybe it's a rare but natural configuration of the local dust environment, interacting with the solar wind in ways we haven't fully modelled. The trajectory adjustment outgassing creates thrust. We know this happens. This object might simply be more active than typical comets we've studied. Under this framework, every anomaly is explainable. We just need more data, better models, and perhaps a bit more imagination about the range of natural phenomena that exist in the universe. The strength of this scenario is its simplicity. It doesn't require invoking anything exotic. It relies on known physics, established chemistry, and the reasonable assumption that we don't yet understand the full diversity of objects travelling between stars. The weakness. It requires accepting a lot of coincidences, the timing of the outbursts, the organisation of the debris, the chemical concentrations, the stable rotation state. Each individual coincidence is possible, but when you stack them together, the probability gets uncomfortable. Scenario 2. It's a panspermia object. This interpretation accepts that the object might not be entirely random. Perhaps it's part of a natural but purposeful process not designed by intelligence, but shaped by the mechanics of how life spreads through the galaxy. Here's the concept. Life emerges on a planet with the right conditions. That planet gets hit by asteroids and comets over billions of years. Some impacts are violent enough to eject material into space material that might contain microorganisms, or at minimum complex organic molecules. That material drifts through interstellar space, frozen, radiation shielded by ice. Eventually, some of it gets captured by passing stars, falling into new solar systems, potentially seeding new worlds with the chemistry or even the biology to jumpstart life. This isn't science fiction. It's a legitimate hypothesis that's been seriously discussed since the 1970s. We know impacts can eject material into space. We've found meteorites from Mars on Earth. We know microorganisms can survive extreme conditions in dormant states. We know organic molecules persist in the cold vacuum of space. What if this object isn't just carrying organic chemistry by accident? What if it's part of that natural distribution system? A comet that picked up concentrated organics from a biologically active system, now travelling through the galaxy. Occasionally depositing its cargo in stellar systems, it passes through the debris trail. Under this interpretation, isn't designed. It's just what happens when an organically rich comet passes through the inner solar system. The chemistry isn't engineered. It's a preserved sample of conditions from another world. The trajectory adjustments are natural outgassing, coincidentally depositing material in stable orbits through the physics of gravity and motion. This scenario has appeal because it explains the chemistry particularly well. Those specific molecules, methanol, hydrogen cyanide, formaldehyde, are exactly what you'd expect from a comet that interacted with a prebiotic or biotic environment, but it still doesn't fully explain the controlled aspects of the behaviour. Natural panspermia should be random, passive. Comets don't choose where their debris goes. They don't time their outbursts for maximum orbital efficiency. They don't maintain stable orientations, unless there's a level of organisation in natural processes we haven't recognised. Unless the universe has mechanisms for distributing life-compatible chemistry more systematically than random chance would suggest. Scenario 3. It's something else. This is the interpretation nobody wants to say clearly, but it hangs over every technical discussion about this object. What if we're looking at something that was made? What if this isn't natural at all? Before you dismiss this as wild speculation, consider what such an object would need to accomplish and how it might be designed. First, it needs to survive interstellar space. Radiation is intense. Cosmic rays degrade materials over millions of years. The solution: coat your probe in ice. Ice is an excellent radiation shield. It's abundant in space. And conveniently, it makes your probe look exactly like a comet. Second, it needs to navigate. Interstellar distances are vast. Even travelling at high speeds, journeys between stars take hundreds of thousands or millions of years. You can't carry enough fuel for constant course corrections. The solution uses gravity assists from the destination star. Dive close, gain speed, adjust trajectory using gravitational interactions, exactly what we see this object doing. Third, if you want to study a system, you need to deposit sensors or samples in stable orbits. The solution: time your material releases to perihelion. Use directional jets to achieve desired velocities. Place payloads where they'll persist for millennia, which is precisely the pattern of debris distribution we're observing. Fourth, you need to avoid detection, or at least avoid raising immediate alarms. The solution: make everything look as natural as possible. Outgas like a comet. Release organic chemistry like a comet would. Behave in ways that have plausible natural explanations, even if those explanations require stretching probability. Does this mean the object is artificial? No. It means the behaviour is consistent with what an artificial object would do if designed to study or interact with a stellar system while maintaining a low profile. The honest scientific position is that we can't rule it out, not definitively, not with the data we currently have, and that's deeply uncomfortable for most astronomers, because accepting this possibility, even as a hypothesis worth investigating, opens doors that are hard to close. It raises questions about who might have sent it, why, whether there are others, what they're looking for, whether we should be trying to communicate with it. Most scientists prefer scenario 1 or 2 because they're manageable. They fit within our existing frameworks. They don't require rethinking fundamental assumptions about our place in the universe. But we don't get to choose which scenario is true based on comfort. We have to follow the evidence. And right now, the evidence keeps pointing to features that are difficult to fully explain through natural processes alone, even as natural explanations remain technically possible. So where does that leave us with more observations needed? With December 19th approaching as a critical moment where better data might definitively favour one scenario over the others, and with a growing realization that regardless of which explanation proves correct, this object is teaching us something profound about what's possible in the universe, whether that's the extraordinary diversity of natural phenomena, the mechanisms of panspermia, or the unsettling possibility that we're not the only ones curious about what exists among the stars. To understand why this object is so puzzling, it helps to compare it with the only other confirmed interstellar visitors we've studied. We've had 3 guests from beyond our solar system in recent years. and each one has been completely different from the others. That diversity itself tells us something important about what's travelling through the galaxy. Let's start with the first one. Oumuamua, October 2017. The name means scout or messenger in Hawaiian. It was discovered by the Pan-STARRS telescope on Maui, moving through our solar system at about 196,000 miles per hour, far too fast to be gravitationally bound to the Sun. Calculations showed it came from the direction of the constellation Lyra, though not from any specific star we could identify. What made Oumuamua extraordinary was its shape and behaviour. Initial observations suggested it was highly elongated, somewhere between 5 to 10 times longer than it was wide. Think of a cigar, or perhaps a flat disc seen edge on. We couldn't tell for certain because we never got close-up images, only brightness variations as it tumbled through space. The tumbling was extreme. Oumuamua rotated completely every 7.3 hours, and the brightness changes were dramatic, varying by a factor of 10. That told astronomers the shape was highly irregular, nothing like the relatively round asteroids we typically see. Then came the real surprise. As Oumuamua moved away from the Sun, astronomers noticed it was accelerating slightly, but not much, but measurably. The trajectory was deviating from what gravity alone predicted. For a comet, that would be normal outgassing creates thrust, but Oumuamua showed no signs of outgassing, no tail, no coma, no detectable water vapour or other gases. Whatever was pushing it remained invisible to our instruments. Dr. Avi Loeb from Harvard proposed that Oumuamua might be an artificial light sail, a thin, reflective surface pushed by sunlight. That hypothesis generated enormous controversy. Most scientists favoured natural explanations. Maybe it was outgassing hydrogen, which is hard to detect. Maybe it was made of nitrogen ice from a Pluto-like world. Maybe solid nitrogen would sublimate without creating a visible tail. Regardless of the explanation, Oumuamua was weird. It looked nothing like objects from our solar system. It behaved in ways we struggled to fully explain. And it left scientists hungry for another interstellar visitor to study one we might detect earlier, observe longer, understand better. 2I/Borisov, August 2019, less than 2 years later. Amateur astronomer Gennady Borisov discovered a comet that turned out to be our second confirmed interstellar visitor. This one was different from Oumuamua in almost every way. 2I/Borisov looked like a normal comet. It had a bright coma cloud of gas and dust. It had a classic tail streaming away from the Sun. Spectroscopic observations detected water vapour, carbon monoxide, and other typical comet molecules. Its shape appeared to be a relatively ordinary 1-kilometre nucleus, irregular but not extremely elongated. It behaved exactly as physics predicted. The trajectory followed a clean hyperbolic orbit with minor adjustments from outgassing that matched the observed gas production rates perfectly. There were no surprises, no anomalies, no mysteries. In fact, 2I/Borisov was almost disappointingly normal. It could have been a comet from our own Oort cloud. The only thing that marked it as interstellar was its trajectory coming from outside the solar system, never to return. Scientists were actually relieved. After the strangeness of Oumuamua, finding a comet that behaved predictably helped establish that yes, normal objects do travel between stars. Not everything from interstellar space is exotic, but 2I/Borisov also raised a question: if interstellar comets can be so normal, why was Oumuamua so weird? 3I/Atlas, September 2024, which brings us to our current visitor. And immediately, you can see it doesn't fit neatly into either previous category. Like Oumuamua, it shows trajectory anomalies that are difficult to fully explain through simple outgassing. But unlike Oumuamua, it clearly has active outgassing. We can see the coma, the tails, the spectroscopic signatures of gas production. Like 2I/Borisov, it looks like a comet and acts like a comet in many ways, but unlike 2I/Borisov, the details are wrong. The chemistry is unusual. The outgassing pattern is too organised. The anti-tail persists when it shouldn't. The rotation state defies easy characterisation. Let me put this in a table format mentally, if you're following along. Oumuamua rocky, or icy, no visible outgassing, extreme tumbling, strong acceleration, highly elongated shape, completely mysterious. 2I/Borisov icy comet, normal outgassing, normal tumbling, predictable behaviour, ordinary shape, completely understood. 3I/Atlas icy comet, active outgassing, stable orientation, controlled acceleration, unknown shape, partially understood with significant mysteries. Do you see the pattern, or rather, the lack of pattern? 3 visitors, 3 completely different profiles. It's almost as if the universe is showing us the full range of what exists out there, the bizarre, the normal, and the in-between. But here's what's nagging at scientists. With Oumuamua, we could at least say, well, it's so different, it's clearly something we don't understand yet. With 2I/Borisov, we could say, this is familiar, a normal comet from another star system. 3I/Atlas sits in this uncomfortable middle ground, familiar enough to seem comet-like, strange enough to resist comfortable explanations. It's almost more troubling than Oumuamua because it looks like it should make sense, and yet the details keep not quite fitting. There's another comparison worth making. All 3 objects was discovered at different points in their journeys through our solar system. Oumuamua was spotted on its way out. We missed the close approach and only caught it as it was leaving. 2I/Borisov was detected months before perihelion, giving us plenty of time to study it. 3I/Atlas was found at an intermediate point close enough to study, early enough to observe the perihelion passage. That timing matters because it determines what we can learn. With Oumuamua, we got limited observations of an object already receding. With 2I/Borisov, we got comprehensive coverage but of something behaving predictably. With 3I/Atlas, we're getting good coverage of something behaving unpredictably. It's almost as if this visitor is perfectly positioned to show us everything we want to see while remaining just ambiguous enough to prevent definitive conclusions. The statistical question is also worth considering. We've now detected 3 interstellar objects in 7 years. That's a detection rate that suggests these visitors are relatively common. Perhaps several pass through the inner solar system each year, with most going unnoticed because they're small, faint, or arrive when our telescopes aren't looking in the right direction. If interstellar objects are common, and if the 3 we've found represent the diversity of what's out there, then the universe is sending us a clear message: expect variety. Don't assume all interstellar visitors will behave the same way. Each stellar system produces its own unique debris, shaped by different formation conditions, different stellar environments, different histories. But there's another interpretation of that diversity. What if these aren't random samples? What if the fact that we've seen 3 such different objects in such a short time frame isn't coincidence? What if something about our current astronomical moment is drawing particular kinds of visitors? That question leads to speculation that makes most scientists uncomfortable. So it's rarely discussed in professional settings, but it exists in private conversations, in late-night discussions at conferences, in the questions researchers ask each other when official statements aren't required. And those questions become more pressing as December 19th approaches, because unlike our previous interstellar visitors, this one is still here, still active, and about to give us our clearest look yet at what came to visit from beyond the stars. Right now, across the globe, telescopes are being prepared, observation schedules have been finalised, teams are coordinated across time zones, ensuring continuous coverage as Earth rotates. December 19th isn't just another date on the astronomical calendar, it's the culmination of months of planning for what might be the most comprehensive observation campaign of an interstellar object ever conducted. Let me walk you through what's actually going to happen and what scientists are hoping to learn. The hardware. The Hubble Space Telescope has dedicated observation time starting at 0200 UTC on December 19th. Hubble operates above Earth's atmosphere, which means no atmospheric distortion, no weather interference, no daylight limitations. Its imaging capabilities in ultraviolet and visible light will capture details of the coma structure and possibly reveal surface features on the nucleus if the gas cloud thins enough. Hubble's spectroscopes will break down the light into individual wavelengths, creating a chemical fingerprint far more detailed than what ground-based telescopes can achieve. Previous Hubble observations of comets have detected dozens of molecular species. With this object's unusual chemistry, scientists are particularly interested in mapping the distribution of organics and looking for anything unexpected. On the ground, the Very Large Telescope in Chile, actually 4 separate 8-meter telescopes that can work together, will provide southern hemisphere coverage. The VLT has instruments capable of adaptive optics, which uses deformable mirrors to compensate for atmospheric turbulence in real time. This allows ground-based telescopes to achieve resolution comparable to space telescopes. The VLT team will focus on high-resolution spectroscopy and polarimetry. Polarimetry measures how light waves are oriented, which reveals information about dust particle size, shape, and composition. If the debris this object is releasing has unusual properties, say, particles that are unexpectedly uniform in size or shape, polarimetry will detect it. The Keck Observatory in Hawaii brings 2 10-meter telescopes to the campaign. Keck specializes in infrared observations, which penetrate dust clouds better than visible light. This is crucial because the nucleus is still shrouded in gas and dust. Infrared imaging might see through that veil to reveal the solid object underneath. Keck will also measure the thermal emission, the heat radiated by the nucleus. Different materials heat and cool at different rates. By measuring how the object's temperature changes as it moves through different solar intensities, scientists can infer composition. Is it mostly ice rocky? Something with unusual thermal properties? Radio telescopes are also involved. The Atacama Large Millimeter Array in Chile, a network of 66 radio dishes working together, will search for molecular emissions invisible to optical telescopes. Radio observations can detect complex organic molecules, measure gas production rates with high precision, and potentially map the 3-dimensional structure of the outgassing jets. There's even a possibility of radar observations. NASA's Goldstone Deep Space Network has planetary radar systems capable of bouncing radio waves off asteroids and comets. At 175 million miles, the object is near the edge of radar range, but if the nucleus is large enough and reflective enough, radar echoes might return. Radar can measure rotation rate directly, determine shape with extraordinary precision, and even detect surface roughness, the measurements. So what exactly are all these instruments looking for? Let me break it down by specific questions scientists want answered. First, what shape is the nucleus? Is it irregular and lumpy like a normal comet, or does it have any geometric regularity, even subtle symmetries, perhaps a slightly cylindrical profile? Or surfaces that seem flatter than natural erosion would create would be significant. Shape tells us about formation processes, internal structure, and whether we're looking at a loose rubble pile or something more coherent. Second, how fast is it rotating, and around which axis? We've discussed the rotation mystery, but December 19th should finally resolve it. Continuous observations over 48 to 72 hours will reveal any periodic brightness changes. Even if the variation is small, just a few % modern photometry can detect it. The rotation period, combined with shape information, tells us about the object's structural integrity and whether it's tumbling chaotically or maintaining oriented flight. Third, what's the exact trajectory, and is it changing astrometry, precise position measurements will be conducted every few hours. These measurements have accuracy better than 0.1 arcseconds, which translates to positional precision of about 100 kilometers at the object's distance. Any deviation from the predicted path, any acceleration spike, will be immediately visible. If the object makes a course correction on December 19th, we'll see it happening in real time. Fourth, what's the outgassing pattern spectroscopy will map which molecules are being released, from which regions of the nucleus, at what rates. Scientists will look for asymmetries as gas coming equally from all sides, or predominantly from specific vents. Are the vents fixed to surface features, or do they activate and deactivate as the object rotates? Does the chemistry change over time, suggesting different ice compositions at different depths? Fifth, what's in the debris? Detailed analysis of the dust tail will reveal particle sizes, compositions, velocities. Scientists want to know if this debris is just normal comet dust, or if there's something unusual about its properties. Are the particles more uniform than expected? Do they have unexpected compositions? Are they being released in organised streams? The timeline observations begin just after midnight UTC on December 19th and continue for at least 72 hours. This isn't a single snapshot, it's a campaign. Different telescopes will hand off coverage as Earth rotates, ensuring nearly continuous monitoring. The data won't be analysed in real time during a single broadcast. Raw data from telescopes requires processing calibration, noise reduction, image stacking. Initial results typically appear within hours for basic photometry and astrometry. Detailed spectroscopic analysis takes days. Comprehensive reports from major observatories usually take weeks. But here's what's different about this campaign: the level of coordination and the plan for rapid data sharing. Multiple research teams have agreed to preliminary data releases within 48 hours of observation. Not full analysis, but initial findings, early images, preliminary spectra. Rough shape estimates. This is unusual. Normally, research teams keep data proprietary while they work on publications. But the level of interest in this object, combined with the recognition that multiple perspectives might be needed to interpret what's found, has created an environment of unusual openness. The possible outcomes. Think about what different results would mean. Best case scenario. From a "this is normal" perspective, the nucleus turns out to be an irregularly shaped tumbling comet with asymmetric outgassing that happens to create the observed acceleration pattern. The chemistry, while unusual, fits within known ranges for comets from different stellar environments. The anti-tail is explained by a particular configuration of dust and solar wind. Mystery solved. Unusual, but natural, middle case. The observations reveal features that are interesting but ambiguous. Maybe the shape is slightly more regular than typical comets, but not definitively artificial. Maybe the rotation is slow but not impossibly so. Maybe the outgassing is organised but could still be natural. We get better data, but not conclusive answers. The debate continues with more information, but no resolution. Challenging case. The observations show something that doesn't fit natural explanations comfortably. A shape that's too regular, a rotation state that's too stable, outgassing that's too controlled, chemistry that's too concentrated. Not proof of anything artificial, but enough anomalies that the natural explanation requires stacking multiple unlikely coincidences. What happens then? How does the scientific community, how does the public respond to data that suggests something genuinely anomalous without providing definitive proof of what it actually is? That's the scenario that keeps some astronomers awake at night, not because they're certain it will happen, but because they're not certain it won't. And we don't have clear protocols for how to handle that kind of ambiguity responsibly. But speculation about outcomes doesn't change what's about to happen. In just a few days, we'll have the data. We'll see what this visitor actually looks like. And whatever we find, it will tell us something important about what exists in the universe beyond our small corner of space. Let's step back for a moment and look at the complete picture we've assembled. An object arrived from interstellar space, moving on a trajectory that should have been perfectly predictable. But it's not following that path. It's making adjustments small, consistent, controlled adjustments that require some kind of thrust mechanism we can't fully explain through chaotic comet behavior alone. It's releasing debris in organized patterns, depositing material into stable orbits that will intersect multiple planets in our solar system for centuries to come. The timing of those releases coincides almost perfectly with the moments when gravitational mechanics would make such placements most efficient. It's carrying chemistry that reads like a recipe for the building blocks of life. Not just random organic molecules, but a concentrated mixture of exactly the compounds you'd need to jumpstart prebiotic chemistry on a suitable world. It's maintaining a feature that shouldn't be stable and anti-tail pointing toward the sun in a configuration that creates what looks remarkably like a thrust stabilization system. And it's doing all of this while showing no clear signs of the tumbling rotation that every natural comet exhibits. No brightness variations, no chaotic outgassing, just steady, persistent, organized behavior. Any one of these features could be explained naturally. Stack them together, and you're forced to accept either an extraordinary series of coincidences or the possibility that we're looking at something fundamentally different from what we've encountered before. Why? This matters beyond science. Most astronomical discoveries, no matter how significant, remain within the scientific community. The detection of gravitational waves was revolutionary for physics, but it didn't change how most people think about their daily lives. The discovery of thousands of exoplanets expanded our cosmic perspective. But in abstract ways, this is different. If this object is natural but exhibits behavior we don't understand, it expands our knowledge of what's possible in the universe. It tells us that nature is more creative, more diverse, more surprising than our models predicted. That's exciting. That's the kind of discovery that drives science forward. If this object is part of a natural panspermia process, it suggests that life's ingredients, perhaps even life itself, spread through the galaxy in ways we're only beginning to recognize. It means the emergence of life might not be isolated accidents on individual worlds, but part of a larger cosmic process that fundamentally changes how we think about our origins and our place in the universe. And if this object is something else, if it exhibits features that resist natural explanation despite our best efforts to find one, then we're confronting the possibility that we're not alone. Not in the distant, maybe there's life on some planet orbiting some star way, but in the immediate, concrete something from somewhere else came here way. That's not just a scientific question. That's a civilizational question, the weight of uncertainty. Here's what's particularly challenging about our current situation. We have enough data to rule out simple explanations, but not enough to definitively support any single complex explanation. Scientists are trained to work with uncertainty. We're comfortable saying we don't know yet. We're accustomed to mysteries that take years or decades to resolve. But there's a difference between not knowing the answer to a purely academic question and not knowing the answer to a question that might fundamentally change how humanity understands its place in the cosmos. The astronomers working on this object are being careful with their language. Public statements emphasize that natural explanations remain possible. Technical papers focus on observational data rather than interpretation. There's an institutional caution about raising public expectations or causing unnecessary alarm. But in private conversations, in late-night discussions at observatories, in the careful phrasing of emails between researchers, there's an undercurrent of not quite excitement, not quite nervousness. Something closer to anticipation mixed with responsibility. A recognition that what they're observing might be genuinely significant. Combined with the weight of needing to be right about something this important, what you need to do, December 19th is 8 days away. As I mentioned at the beginning, we're posting live coverage as the observations happen and initial data becomes available. This is going to be a real-time event. You need to be here for it. But beyond just watching, I want you to think about what different outcomes would mean to you. How would you process the confirmation that this is just an unusual but natural comet? Would that be disappointing or reassuring? How would you react to evidence that it's part of a panspermia process? That the universe has mechanisms for spreading life's ingredients between worlds? And how would you think about your place in the universe if the evidence points towards something we can't easily explain through natural processes? These aren't idle questions. In 8 days, we might have answers that require us to genuinely engage with them. The immediate future. Starting December 19th, data will begin flowing from telescopes around the world. Images will be processed. Spectra will be analysed. Trajectories will be refined. And within 48 to 72 hours, we'll know significantly more than we do right now. We'll see the shape of the nucleus, or at least a better approximation of it. We'll have rotation data, or confirmation that rotation remains undetectable. We'll have precise trajectory measurements showing whether any course corrections occurred. We'll have detailed chemistry maps showing what this visitor is really made of. Those are facts we'll have. What those facts mean, that's the interpretation that will take longer. But the facts themselves will be available, and they'll constrain the range of reasonable explanations. Maybe we'll find that everything fits a natural comet model better than we thought. Maybe we'll find evidence that clearly supports panspermia. Maybe we'll find data that makes the mystery deeper rather than resolving it. Regardless of the outcome, this is a moment worth paying attention to. We're watching an object from beyond our solar system during its closest approach to Earth. We're applying the best observational technology humanity has ever developed. We're asking questions about what this visitor is and where it came from and what it might mean. And in a few days we'll have answers. Not complete answers. Perhaps not answers that resolve every question, but more information than we've ever had before about what travels through this darkness between stars. Your role in this. Before I close, I need you to do 3 things. First, if you haven't already, subscribe to this channel and turn on all notifications. The December 19th coverage is going to be unlike anything we've done before. You need to be here when the data starts coming in. Second, share this video. Most people have no idea this is happening. An interstellar object exhibiting unusual behaviour, approaching Earth for its closest pass, about to be studied by every major telescope humanity can aim at it. This is the kind of event that matters. People deserve to know about it. Third, drop a comment with your theory. After everything we've discussed, the trajectory anomalies, the debris pattern, the chemistry, the anti-tail, the rotation mystery, what do you think we're looking at? Natural comet panspermia? Object. Something else entirely. I want to hear your thoughts. And more importantly, I want you to commit to an opinion now, before the data comes in, so you can see how your thinking changes based on what we learn. December 19th, 8 days. The countdown is running. Whatever we discover, we're going to discover it together. Thanks for watching. I'll see you when the observations begin.